Welcome to lecture 31, 8.1, distribution of the sample mean. Okay, let's look at an example. Suppose that you took a simple random sample of 200 students at Windward Community College and found that the mean number of credits they were taking this semester was 9. However, if you took a different random sample of 200 students, it's likely you would end up with a different mean number of credits, such as 12. A third random sample might lead you to getting another mean of maybe 7, and so on. You could get a number of different mean values depending on the sample that you take. Okay? So because the students vary from sample to sample, this means that the mean will also be varying from sample to sample. Due to this, the sample mean, x bar, is a random variable. And due to this, that means it also has a probability distribution. So our new goal now is we're going to describe this distribution of the sample mean. Let's take a look at the definition. All right, so the sampling mean, actually distribution, sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. So the sampling distribution of the sample mean, which we know as x bar, is the probability distribution for all possible values of the random variable x bar, computed from a sample of size n, from a population with mean mu and standard deviation sigma. Okay, so how do we obtain a sampling distribution of the sample mean? Well, 3 steps. First, obtain a simple random sample of size n. Then you're going to compute a sample mean. Assuming we are sampling from a finite population, okay, so that's pretty important, a finite population, we're going to repeat steps 1 and 2 until all distinct simple random samples of size n have been obtained. Okay, so once a sample has been obtained, it cannot be obtained a second time, so you cannot obtain it a second time. Alright, so let's take a look at the objective 1. Describe the distribution of the sample mean, or the normal population. For a normal population. Okay, so refer to the video located in the La Lima resources under the tab named StatCrunch Video Help, as well as read example 1 and 2 in your book. That goes over the StatCrunch way of finding the distribution of the sample mean. So by taking a bunch of different sample means from your data set. And always email me if you have any questions about how to do that. Alright, so the mean and standard deviation of the sampling distribution x bar. Suppose that a simple random sample of size n is drawn from a population with mean mu and standard deviation sigma. The sampling distribution of x bar has a mean of mu x bar equal to mu and standard deviation of sigma x equal to sigma divided by the square root of n, your sample size. And the standard deviation of the sampling distribution of x bar, which we call sigma x bar, is called the standard error of the mean. Now, the shape of the sampling distribution of x bar, if x is normal, okay, once again, we're taking a look at when x is normal here. So if a random variable x is normally distributed, sorry, the handwriting's not coming out that nice. I have a little silencer in my pen now, so I'm not making a bunch of tapping sounds the whole video, but it is sort of screwing with my writing. Not the best. All right. So if the random variable x is normally distributed, then the sampling distribution of the sample mean x is going to be normally distributed. All right, So let's take a look at example 3. A simple random sample of size n equals 49 is obtained from a population with mu equal 49 and sigma equal 18. What is the probability of x bar being greater than 83? So what do we want to do here? Well, if we want to go ahead, we should convert this to a z-score. And then we can find the area to the right of the z-score. And when we've done that, we could go ahead, so let me go ahead and draw this. If we find the area to the right, well, we want the area to the right. And to do that, first we'll find the z-score, which will give us the area to the left. And then we can subtract that from 1, and we'll find the area to the right. That is our plan. So in order to do the z-score, we need the mean and standard deviation. So mean, in our case, is just going to be equal to the mean that's given, which is 80. And then our standard deviation of x is going to equal, we're going to take our sigma and divide that by the square root of our n value, which is, well, it's going to be 49. So that'll be 14 divided by the square root of 49, which is going to come out to be 2. Ooh, what a nice number. That's unusually nice. Okay, so now what do we want to do? Well, remember, we're trying to find that z-score. Then we can find the area. Once we find the area, which will give us the area to the left, we'll subtract it from 1 to get the area that is greater than, which is what we're looking for. Remember, for 83, we're looking for a greater than. Okay, so we're going to go ahead and turn this into a z-score. That will be x bar minus mu x bar all over sigma x bar. Our x bar here is going to be 83 minus our mu, which is 80, and dividing that by standard deviation, which is 2. So that'll come out with 3 divided by 2, so z is going to be about, or actually exactly, 1.5. Ooh, that's nice. Okay, so we're going to go ahead and look in table 5 of our book to find the area to the left of 1.5, and what will we get? So area to left is 0.9332. But remember, we don't want the area to the left because we're looking for x to be greater than 83. We're looking for the area to the right. So to find that, we're going to do 1 minus 0.9332. And what will we end up with? We'll get 0.0668. All right, so this is not a word problem, so we can just answer with p of x greater than 83 is going to equal 0.0668. Now let's take a look at the next one. Go ahead, try see if you can solve B by yourself and check back in with me in a second. All right, so we're trying to find P of x bar, which is less than or equal to 75.8. Well, we've already found the standard deviation and the mean for our problem, so we'll just go ahead and translate this into a z-score to find the area. So we're using 75.8 as our x bar value, then minus 80, which we already have, divided by 2. So once again, the 75.8 comes from that value there that we're trying to find. So translating to a z-score, we're going to end up with z equals negative 2.1. Okay, so the area to the left of z equals negative 2.1 is what? What's that area going to be? So negative 2.1. Let's see, looking at our chart, we'll get 0.0179. Okay, and notice we're already trying to find the area to the left because we want it to be less than. So that is actually going to be our value we're going to solve for. So the probability of x bar being less than or equal to 75.8 is going to equal 0.0179. Now let's take a look at objective 2. Describe the distribution of the sample mean when we have a non-normal population. Okay, so switching gears here. Note, for any population, regardless of its shape, as the sample size increases, the shape of the distribution of the sample mean becomes more normal. And that leads us directly to something called the central limit theorem. All right, so regardless of the shape of the underlying population, the sampling distribution of x bar becomes approximately normal as the sample size of n increases. So we have a question. How large does the sample size need to be before we can say that the sampling distribution of x bar is approximately normal? So if you want, you can take a look at the book on page 374, and it gives you a few examples visually of kind of what happens as you take larger and larger sample size. But basically, as your sample size gets larger and larger, it slowly starts to look like a normal bell curve. And the rule of thumb that was sort of just agreed upon by the statisticians was that, here we go, if the distribution of the population is unknown or not normal, then what happens next? The distribution of the sample mean is approximately normal, provided the following. So provided, and here's where the magic happens, provided that the sample size is what? Greater than or equal to, and here's the drum roll, 30. And you can take a look in the book and see what happens, but basically as you start to slowly end up with mean closer and closer to 25, it starts to look pretty much like the normal curve. But to be safe, people bumped it and said, let's go ahead with n equal to 30. Alright. So now let's take a look at example 5. The mean weight gain during pregnancy is 30 pounds, with a standard deviation of 12.9 pounds. Weight gain during pregnancy is skewed right. An obstetrician obtained a random sample of 35 low-income patients and determines that their mean weight gain during pregnancy was 36.2 pounds. Does this result suggest anything unusual? Well, what are we trying to find out here? We're trying to see if anything unusual is from what she's found. So in order to do that, we're going to go ahead and determine the likelihood of obtaining a sample that has a mean of 36.2. So like if we had randomly picked a bunch of people, how often would we end up with a mean of 36.2? That's what we're trying to find here. Alright, so to do this, we're going to go ahead and turn this into a z-score. But in order to turn this into a z-score, we need mu and standard deviation. So mu of x is going to equal our mu value, our mean value, which is going to be 30. And then our standard deviation of x bar, that's going to be standard deviation divided by the sample, which is 12.9 divided by our sample of the square root of 35. So we end up with our standard deviation coming out to approximately 2.18. Okay, so now we can use this to go ahead and find our z-score. So z-score is going to equal, well, our x bar, which is going to be what? Well, remember, we're looking for the probability of x bar being greater than 36.2 or equal to. So then we go ahead and erase that and write that a little neater. So being greater than or equal to 36.2. So on the z-score we have 36.2 minus our mean, which is 30, and divided by our standard deviation, which is about 2.18. And that comes out to be approximately 2.84. Alright, so we're going to go ahead and take a look at table 5 to see what value we get. So let's see, the area to the left of 2.84, or from z equals 2.84, is going to be what? 0.9977. But remember, we're looking for the area to the right. We're looking for greater than. So to find that, we're going to do 1 minus the 0.9977, and that gives us, let's see, plugging that into the calculator, we get 0.0023. Now what is this saying? This is saying that the probability of a random sample of 35 women with a mean weight of 36.2 pounds, okay, so let me see that, pounds, is about 0.002. Okay, because remember, this is talking about the different possible sample sizes that we pick and the mean for each sample. So if we have a random sample of 35, we're trying to figure out what's the probability of having 36.2 be our mean. And according to the data we found, the probability of finding this kind of an occurrence is 0.002. That is a really small probability of ending up with 36.2 being a mean. Alright, so that's not pretty normal to have 36.2 be a mean. So what can we conclude what we found here? Well, remember, the sample that was picked was all women that came from low-income backgrounds. So something that we can conclude is that the mean weight for low-income patients is more than 30 pounds. Okay, just something we could possibly conclude from the data that we've just found. Alright, now let's take a look at the summary. So just a few little charts here. So the summary for shape, center, and spread of the sampling distribution of X. So remember, we have two different options. We have that it's normal or that it's not normal. So first off, if the population is indeed normal, with a standard deviation of sigma and a mean of mu, what can we do? Well, the shape, so regardless of sample size n, the shape of the distribution of the sample mean is normal. So what do we know about the center of the sample mean? It's going to be mu of x bar equals mu, and sigma of x bar is going to equal sigma divided by the sample size. Next, if we have the population is not normal with mean mu and standard deviation of sigma, well, what we can do is, even though it's not normal, we know that as the sample size of n increases, and remember we want n to be greater than or equal to 30, the distribution of the sample size becomes approximately normal. And once it's approximately normal, we can kind of use the formulas for the normal curve. So we have mean of x bar is equal to mu, and sigma of x bar is going to equal sigma divided by square root of n. Alrighty, so as usual, one of the main things here for when we have a non-normal curve, you just need to check that your sample size is greater than 30 before you can go ahead and use the formulas on the right. Okay, that is it for 8.1. Please email me if you have any questions with the homework.